Hello, hope you can hear me okay. Uh, we're in the lab, so there might be some humming from the hoods. This is the review session for Monday, October 28th at 3:30. In class, we did roadmaps, and today I'd like to try something different. I want to see how this looks, all these reactions look like in terms of lists. And so for this first video, first maybe 30 minutes, I want to look at Module 7, radicals. It turns out that the classes divide very evenly between modules. There are 2 classes per module. So for Module 7 of radicals, we have Class 17. Our first reaction in Class 17 is going to be obviously reaction 17A. And I like to label my reactions with a name. 17A is radical halogenation. And the idea here is to give maybe an easy example and maybe a harder example. We're not going to go through the mechanisms, but we'll definitely note whether you need to know the mechanisms or not. For instance, the overall reaction is if you have an alkane or cycloalkane, for instance, this. Let's try that. You could add Br2 with either heat or light, and you'll get a product. Maybe a harder example is maybe if we have these rings like this. And then either we could use light or heat. So let's, in this case, use heat. For this radical halogenation, you should only use Br. So only use Br2. And I'm going to note here that we need to know the mechanism. Let me use a different color. We need to know the mechanism. This is the mechanism where you have the 3 steps, right? The initiation, propagation, and termination. Initiation has 1 step. Propagation, and termination. Underneath, I'll put a number of steps. There's 1 initiation, there's 2 propagations, and there happens to be 3 terminations. Stereochemistry, right? Your radical is flat. So there's a possibility that you might have racemic mixture. The radical intermediate is flat. Right, you know that carbon is sp2 hybridized, and so possible racemic. I don't know if we're going to see that in these examples. Okay, you could pause the video if you want. Try to fill in the products for these 2 examples. All right, for the first one, we have this bromine right here. You cannot put a bromine here. There's no hydrogen to abstract. So know that terminology. We abstract a hydrogen. So 1 step is hydrogen abstraction. It's useful to have these terms written out so you're not surprised by them. Hydrogen, it's called abstraction. Oops. It's basically you're removing a hydrogen. Again, we're not doing the mechanism. but you should be able to find the hydrogen abstraction step. It's the first step in propagation. There's no chiral carbon here, and therefore there is no racemic mixture. For the other example, again, you can't put the bromine here. There's no space. We do have a tertiary carbon, so you're putting the bromine at the most substituted position that has a hydrogen that can be abstracted. You know, this position that has 4 bonds already, this one right here, that's called a quaternary, like a 4 degrees. This one here, quaternary and no hydrogen. So we're going to put the bromine on the tertiary, right? And that tertiary has, obviously, that's the most substituted spot that had a hydrogen to abstract. And so the hydrogen that was abstracted, we could literally draw it here, that one, and this one. Okay. Looking through the handout, you should be doing this on your own. Look through the handout, see if there are any special considerations. We talked about the racemic mixture possibility. I don't think there's anything else that we need to talk about in this case. All right, any questions about the radical halogenation? You want to number these? I don't think it's necessary to number. We already have the notation here. 17A. Right, this is what you should be doing at home. Once you're done with 17A and you're pretty confident, you can move on to 17B. 17A. Let's look at 17B. Reaction. 17B. That is allylic halogenation. Don't forget, this was the handout where I made it so it's simpler. In allylic halogenation, you have to be able to identify the allylic carbon. And so, what do I want to put here? Oh, why don't we put this? Whoops. Oh, that's bad news. The screen just went out. Oh, there we go. I think we should put up here alkane, so we know the starting material. So these are either alkanes or cycloalkanes. That's A and E. Okay, let me make this clearer. Alkane, and this is cycloalkane. You might have heard me say that there's only one road out of alkane or out of Kennesaw. That's Br2 and light. Only one road. So this allylic halogenation is of an alkene. And so I'll draw any alkene. Let's draw this one here. Symmetrical. We use a special reagent called NBS, and NBS also uses light or heat. That tells me that it's radical. Okay, whenever you use light or heat, it's a radical reaction. Meaning that we're going to form a radical intermediate. Okay, I like to label the allylic carbons. I think there was a little bit of misunderstanding in class. The arrows tell me that these are allylic, this carbon and this carbon. But then I labeled it A. A does not stand for allylic. A means this is the first allylic carbon that I see, but it's also identical to this allylic carbon, so I give them the same letter. If the bottom carbon was a different allylic carbon, like if it wasn't symmetrical, I'd label this B. Okay, so that's one. And then the harder version might be something like this. Let's see. The harder version would have at least 2 different allylic carbons. How about this one? I don't think I've tried this one before yet. That. Okay. plus NBS would heat. Okay. So what are some notes before we look at the reaction? Do you need to know the mechanism? Not really. So let me write that down. Do not need to know full mechanism. What do you need to know? You need to know how about this? You need to know, we'll call this the initial radical, the first radical you make, and its resonance. Okay. So this is going to be a little bit tricky. You could always recopy your notes. But let me move this down a little bit. Okay. The shortcut. Let me show you how to do it the fast way. Okay? The fast way is the first product is you put the bromine exactly where the arrow is pointing at, right there. And you keep the double bond because you're forming what's called an allylic bromide. So all of these products will be the allylic bromide. And we have two in this case, I think. Okay. So do you see how all I need to do is put the bromine on this pink dot? Okay. If you're curious as to why, we could draw the intermediate. The intermediate is what we call do you see how I wrote here? The initial radical. I'm not too happy about the handwriting. Okay. So the initial radical is literally, you remove the hydrogen that's on this carbon, and you form a radical. And you see how that gave me this product. But that radical has resonance. And we have to decide whether that resonance contributor is going to give us the same or different products. Okay. I'm not drawing the mechanism, but I'm showing you how you could get the other contributor quickly. You move this pi bond towards the radical to make the pi bond here. Again, you move the pi bond to here. That makes this carbon naked, this one. So after you move the pi bond, this carbon is naked. These are your intermediates. Why don't you challenge yourself? Maybe your classmate is confused. How did I go from here to here? Because we're using fish hooks, it actually takes quite a bit of arrows. For instance, you move this electron here to the bond. Okay, so that's a little bit close, but that's to the bond. You move this pi electron here to complete the pi bond. And then that pi bond has a second electron, you put it directly onto that carbon. That's how you get the radical in that position. Once you get that radical in that position, you'll notice that it gives you a different product. Just put the bromine where the radical is. Remember, your double bond has shifted, and you have these two methyl groups. Okay. So the answer, if I wanted the product, is in blue. Normally, I would ask which is the more stable. You look at the more stable alkene, and it's this one here. Okay. Why do I say that's the more stable alkene? This one is tri-substituted. You have a hydrogen here. Every double bond has 4 positions. If one of them is hydrogen, the other 3 tri are substituents. You could do the same trick here for the one on the left. We have 2 hydrogens, so the out of the 4 positions, 2 of them are hydrogens, 2 of them are substituents. This is called di-substituted. Di. Okay. Hopefully, most everyone can do something like that to get the 2 products. Double check that they're not identical. If they're not identical, you should be able to determine who is the stable, more major product. Okay. I'm not going to go through the radical intermediates for the second one, okay? But I am going to show you, I am considering this allylic position and this allylic position. So we have A and B. Without drawing the green, if you still need to figure out, or if you still need some clarification how I got this, come see me in drop-in hours. But let me show you how fast you can do this. The initial radical is here. Put the bromine there. Make sure you have a bond. Okay? Plus. Imagine if this double bond shifted towards the radical. There will be a double bond here, and then there'll be a radical here. Put the Br there now. Okay, without drawing the resonance, if you can remember, the double bond shifted, and now the radical's there, put the bromine there. All right. Before I move on, I just realized those 2 are identical. Do you know that's identical? They're identical because if I rotate this bond right here, I could get this double bond here, and I could get this group down here. These are identical. Wasn't expecting that. What about for radical B? Again, we're going to do this the fast way. This is on video, so you can always rewind it, or you could come for me for clarification. Look at B, right there. So put the bromine right here. That's our first product. Put the bromine right there. Okay? Now I'm going to draw it. Imagine if there was a radical right here. See on the left, this one right here? Well, if I shift the pi bond this way, the radical will now be on this carbon. So try to memorize, or try to remember that the radical is on the N carbon, the double bond had shifted to the right, and the bromine now is here. Those are your 2 products for the B radical, and let me erase the radical here on the left, this one right here. Okay. All right. I know that was a lot. You could always double check. How do you double check? Do you see this in purple? All the products are allylic. All of these are allylic. See, that's an allylic carbon. That's an allylic carbon. That's the allylic and allylic carbon. This is allylic. So all allylic bromines. The major product for the B is this, and for A, they're identical. So I don't know, circle both of them. You are circling the molecule per pair. So you compare these 2, circle the major, they just happen to be identical. Compare these 2, circle the major, this is tetrasubstituted. Everything I've said in this video, this is for class 17, everything I said in this video should be recognizable. If any term I used is not recognizable, then you have to let me know. Reaction 17B. All right, we're checking the handout. Make sure there's nothing that important that we missed, but that's the 2 reactions. Let me stop there. This is the review for, I guess, class 17. It took about 30 minutes. Any questions about this? Your 2 reactions are there. Everything you need to know is here, except for the full mechanism. The full mechanism you need to know is for the radical halogenation. Okay, any questions? Okay, good. In the next video, we'll do a review. We'll do a study sheet for class 18. That's the one with, I think, the non-Markovnikov edition of HBR.